Welcome to Lecture 1.4, Binomial and Multinomial Coefficients. To motivate this topic, recall the number n choose k that we saw in the previous lecture. That's called a binomial coefficient, and it counts the number of k-element subsets of an n-element set. And remember that n choose k is equal to n factorial over k factorial times n minus k factorial. The binomial coefficients, these actually satisfy a remarkable number of properties. In this lecture, we will explore these and generalize them to something called the multinomial coefficients. In a later lecture, when we look at combinatorial proofs, we will see a whole bunch of formulas and identities involving these things. As a teaser, the entries in Pascal's triangle, this is something you've probably seen before, are actually binomial coefficients. So remember what Pascal's triangle is. So it's this triangle, looks like this, and it has a property that each entry is just the sum of the two entries above it. And if we're on the border, so each of these ones is just the sum of the one above it. So we start with the 1, and then we make all of these outer entries 1. If you want to think of this 1 as 1 plus 0, that's fine too. Or you can just start with that boundary, and then the 2 is 1 plus 1, the 3 is 1 plus 2, 3 is 2 plus 1, the 6 is 3 plus 3, the 4 is 1 plus 3, the 4 is 3 plus 1, the 1 is just 1, and 5 is 4 plus 1, and so forth. Okay, so this is something you've probably seen before, but what you likely have not seen is this. The entries in this triangle are just the binomial coefficients. So some of these are easy to check. All of these entries, n choose n is just equal to 1. And I should say that if you call this first row the 0th row and these entries the 0th entries in each row, then in row n, the kth entry is n choose k. So we can see why n choose n equals 1. There's one way to choose n things from a set of size n, and similarly there's one way to choose nothing from a set of size n. So the outer ones hold, and similarly 0 choose 0 is 1 because there's one way to choose nothing from an empty set. If you don't believe that, 0 factorial over 0 factorial times 0 factorial is equal to 1. Because 0 factorial is equal to 1. And then, well, to verify this, all you have to do is show that, well, since we have the boundary, to show that the remaining thing holds, we just have to show that the same, we call this a recurrence relation holds, that each entry is just the sum of the two above it. In other words, that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So if we can show that these two things, the sum of these two things equals n choose k, then it follows immediately that this triangle is exactly what we want. Okay, so let's do that next. Okay, so here it is formalized as a theorem. The binomial coefficients satisfy the following recursive formula. N choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k for all positive n and all n between 0, all k between 0 and n. So I didn't say that n and k have to be integers, but I think it is clear from the context that is what is meant. So one way to prove this is algebraically to explicitly show that the left-hand side, which is this formula, is equal to the right-hand side. So how would you show that? I'm not going to do it, but I'll give you a hint. If you want to add these two fractions, so you somehow want to add these two things and show that they're equal to this, so find a common denominator. And this is almost the common denominator, so to make this the same, if you multiply by k, then this becomes k factorial, and if you multiply this by n minus k, so if you multiply top and bottom by k, and multiply this by n minus k, top and bottom, then this becomes n minus k factorial, and actually this is pretty short. So now the bottom of this is is k factorial times n minus k factorial. And the top of this, look what we have. We have, how many n minus 1 factorials do we have? We have k plus n minus k. So that is n times n minus 1 factorial. And look what we have. We have n, so this is just n factorial, which is that, and the bottom is equal to that. So that's one proof. It's pretty short. Here's another way to prove it, using something that's called a combinatorial proof instead of an algebraic proof. So what we'll do is if we have this identity up here, if we can find something which is counted by the left-hand side and by the right-hand side, then these two things have to be the same. So notice that the left-hand side counts the number of ways to elect k candidates from a pool of n. So if we can somehow cleverly figure out how to count the same thing using not this formula but this formula, then we know that those formulas have to be the same. So for the second method, the first method is just n choose k. We know how to do that already. Assume that we have n candidates, but one of them is distinct. One of them is special in some way. You can either say special in a good way or special in a bad way. So how many ways do we have to elect k candidates? Well, there's case one, where we elect the special candidate to our pool of n. In this case, then what's left? We have k minus 1 remaining choices among n minus 1 choices. Then there are n minus 1, k minus 1 ways to pick the remaining seats, say. And then case 2 is we don't elect the special candidate. In this case, now we still have to elect k candidates, but now our pool is n minus 1 because we know that we are not including our special candidate. So there are n minus 1 choose k ways to pick or to fill the remaining seats. So all in all, the total number of ways to elect k candidates is n minus 1 choose k minus 1 plus n minus 1 choose k. So in total, n minus 1 choose k minus 1 plus n minus 1 choose k. So since we have two different ways to count the same thing, the number of ways to elect k candidates from a pool of n, one of them is just n choose k, which we know and love, and the other one is this way, then those have to be equal. So that's called a combinatorial proof. More on this later. Now we come to something called the binomial theorem, and we will motivate this with an example. Notice that if you take x plus y, two variables, raise it to the 6th power, and you multiply it out, you get x to the 6th plus 6x to the 5th times y plus 15x to the 4th y squared plus 20y cubed x cubed plus 15x squared y to the 4th plus 6x y to the 5th plus y to the 6th. I'll let you check the details if you want, but let me ask you, do these numbers here, these coefficients, look familiar? They might, because they are binomial coefficients. So let's formalize this. We'll call it a theorem. It's for any variables x and y and n at least 1. I think it holds for n equals 0 too, but it's pretty trivial. So we'll just focus on this. X plus y to the n. Well, if you multiply this out, you get a whole bunch of terms, and all of those terms, notice that the exponents add up to n, so 6 plus 0, 5 plus 1, 4 plus 2, 3 plus 3, so forth. So you got a whole bunch of terms of the form x to the k, y to the n minus k, because these add up to n. And the coefficient of this is n choose k. So formally, x plus y to the n is the sum from 0 to n of n choose k times x to the k times y to the n minus k. So basically it's saying that this thing holds for all n. So this connects this expansion with the rows in Pascal's triangle. And it's called the binomial theorem because these are binomial coefficients. Okay, so let's think how we can prove something like this. I say prove, I really mean just verify. Let's start by multiplying out or foiling. Remember this acronym? First, outer, inner, later. If not, all the better. The product x plus y to the n. So here we have n copies of x plus y, like this. And think about what happens when you multiply this out. So I don't expect you to come up with something like this, but just qualitatively. You get 2 to the n terms. And all of them are going to be distinct length n words or strings in x and y. I think the easiest way to convince you of this is just to show you. For example, for n equals 6, let me write it up here. We get x plus y times x plus y times x plus y. I'm going to do this quickly 6 times. Here's the fifth one, and x plus 6. So if we multiply this out, think about how you would do this. You would take this x and multiply by that x times this x times this x times this x times that x, and you get x to the 6. But you'd also have to multiply by this x times this first 5 x's and that y. So that's going to get you x to the 5th times y. And then you'd also multiply by the first 3 x's, and then the last 3 y's. So you're going to get a term like that. That's going to give you x cubed, y cubed. But you are also going to get an x, y, x, y, x, y. You'll get a term like that. That's going to give you x cubed, y cubed. And you're going to end up getting 2 to the n terms. Again, 1 for every possible word in x and y. Because you're multiplying one of these 2 terms times one of these, so either an x plus y times an x plus y times an x plus y, and so forth. And so the coefficient, so if you go up here, the coefficient of, say, x cubed, y cubed is the number of words in x and y that have length 6 words that have 3 x's and 3 y's. Now, how many of those are there? Well, it's easier to see if you, instead of x and y's, if you write these as zeros and ones, so 0, 0, 0, 0, 0, 0, 0, 0, 0. And now these things are describe subsets of size of a 6-element set. So this is 0, 1, 0, 1, 0, 1. This is 0, 0, 0, 1, 1, 1. And so now this coefficient is the number of size 3 subsets of a 6-element set. And we know that that is 6 choose 3. Okay, so to summarize, there are n choose k words with exactly k instances of x in it. Easier to see if we're talking about binary strings with k instances of 1. And when I say words, I mean length n words, where k instances of x and the remaining letters are y. So this is precisely, n choose k is precisely the coefficient of x to the k times y to the n minus k. Now, one last thing I want to mention is this identity that we just verified holds for all variables x and y. So x and y are anything. So we can plug in numbers for these. So imagine what happens if you take x equals y equals 1. So the left-hand side, if we do that, is 2 to the n. And the right-hand side, these just become 1 to the k times 1 to the n minus k, and we get the sum from k equals 0 to n of n choose k. So what that is that says if we add up all of these binomial coefficients, in this case, we get 2 to the 6, which is 64. And that should be a little bit surprising for you. You probably didn't expect that if you add up the entries in the nth row of Pascal's triangle, you get 2 to the n. So this is what we say is a corollary. It follows from the previous theorem. The nth row of Pascal's triangle sums to 2 to the n. So remember, the nth, if you add up the entries in the nth row, you get n choose 0 plus n choose 1 plus all the way up to n choose n. So the proof of this, what I just told you in the previous slide, and so here it is written out, just take the binomial theorem and plug in x and y equals 1. And as we saw, it falls right out. So that's one proof. But let me go back and show you a combinatorial proof. And now recall what a combinatorial proof is. It's a proof that two things are equal, say the left-hand side and the right-hand side, by showing that they both count the same thing two different ways. So it's not clear how to start. What is going to be counted by this? Well, the left-hand side is hard. So let's look at the right-hand side. What are things that are counted by 2 to the n? Well, one thing is the power set of an n-element set. So let's try enumerating the power set of an n-element set two different ways. The first way, let's just count the number of length n binary strings. This is sort of like what we did earlier when I think I called them true-false questionnaires, but for example, if you have the subset of, say, n equals 6 again, 2, 3, 6, that subset's going to correspond to the binary string 0, 1, 1, 0, 0, 1. So this is 2, 3, 6. This is a 1 in position 2, 3, and 6. Okay, so one way to count the number, or one way to enumerate the power set is just count the number of length n binary strings, and we clearly get 2 to the n. And here's another way to count the number of subsets of an n-element set. Let's group them by size. So let's first say how many size 0 subsets are there? Well, there's going to be n choose 0. Now, how many size 1 subsets will there be? Well, there's going to be n choose 1. Now, how many size 2 subsets? Well, there's going to be n choose 2, all the way up to the number of size n subsets. Oops, I fixed that. That's going to be n choose n. So if you want to add up the number of total subsets of this set, of an n-element set, we can just group them by size. Let's first add up the number of size 0 subsets, and then add to that the number of size 1 subsets, then add the number of size 2 subsets, all the way up to the number of size n subsets. And if you do that, what you're doing is you're adding up the binomial coefficients from n choose 0 all the way up to n choose n. So that is the left-hand side of this equation. And we already know that the number of elements in the power set of an n-element set is the right-hand side. So we've counted the same thing, the size of this power set, two different ways, so those things must be equal. So I really like both of these proofs, and I'll let the choice be up to you as to which one you think takes the cake, because I think they're both really neat. Let me just finish this slide by reminding you that a proof that establishes an identity by counting a carefully chosen set two different ways is called a combinatorial proof, and more on this later. Our next topic are multinomial coefficients, which are natural generalizations of binomial coefficients. So I will motivate this with an exercise. So consider a police department of 10 officers Suppose that they want to have 5 patrol the streets, 2 doing paperwork, and 3 at the donut shop. How many ways can this be done? So I'm no longer picking just 5 from 10. I'm picking 5 from 10 to do one task, 2 from the remaining 5 to do another task, and then 3 from the remaining 3 to do the third task. So to do this, let's see, we have 10 choose 5 ways to pick the 5 officers to patrol the streets. Then we have 10 minus 5 officers remaining, and we want to pick 2 of them to do paperwork. And then we have 10 minus 5 minus 2 officers left, which is 3. We have to pick 3 of those 3 to go to the donut shop. Okay, so the answer to this question is 10 choose 5 times 5 choose 2 times 3 choose 3. Maybe you don't quite see the pattern here as nicely as you did when I wrote it out a few moments ago, but if I multiply this out using factorials, I think you will see a different pattern. This is 10 factorial divided by 5 factorial times 5 factorial times 5 factorial. Notice these 5 factorials cancel. Divided by 2 factorial times 3 factorial, and that 3 factorial cancels with this 3 factorial, divided by 3 factorial times 0 factorial. So we get 10 factorial, that's the total number of officers, permutations of those, divided by 5 factorial times 2 factorial times 3 factorial, which is 2520. Note that this is the same as counting the number of distinct permutations of the following 10-letter word, where we have 5 S's, 2 P's, and 3 D's. So for example, this is one permutation, but I can also do S, P, S, D, D, P, S, S, D, P. And so think of this as the officers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I am delegating them duties. So this first one says that the first five officers have street duty, the next 2 have paperwork duty, and the last 3 go to the donut shop. And this one says officer 1 does the streets, officer 2 does the paperwork, officer 3 does the streets, 4 goes to the donut shop, and so forth. So the number of distinct words here that you can form is precisely what we are trying to count. Now that we understand what these things are, let's define them formally. So suppose that n1 up to nr are positive integers that add up to n. Then the following object, it looks like a binomial coefficient. It's got an n up top, but on the bottom it's got a list, n1 up to nr. I'll skip ahead. That is called a multinomial coefficient. And that is equal to, one way to think of it is n factorial divided by the product of n1 factorial times n2 factorial all the way up to nr factorial, like we did up here. Or you can think of it as the product of binomial coefficients. N choose n1 times n minus n1 choose n2 times n minus n1 minus n2 choose n3 all the way up to n choose or n minus the sum of the first r minus I ni's choose nr. Okay, so several ways to define it. Given this might be better if you're thinking of officers, and this might be better if you're thinking about words. These are called multinomial coefficients, and binomial coefficients, notice, are the special case of r equals 2. So using this notation, we would actually write a binomial coefficient as n choose k, comma, n minus k, but that's kind of silly. There's no reason we would ever do that when we could just instead write n choose k. Let's write down the main points of what we just talked about. Let's consider an alphabet with r letters, like S1 up to SR. The number of length n words, or maybe strings if you're a computer scientist, that you can write using exactly n1 S1s, n2 S2s, all the way up to nr SRs. We, of course, assume that these and i's add up to n, is a multinomial coefficient. So it's n factorial divided by n1 factorial times n2 factorial all the way up to nr factorial. Let's do some examples. First, the number of distinct permutations of the letters in the word Mississippi, or equivalently words you can form by rearranging these letters, or strings you can form with one M, four S's, four I's, and two P's, equivalent ways to say the same thing, is the following multinomial coefficient, or just n factorial over 1 factorial times 4 factorial times 4 factorial times 2 factorial, which is 34,650. And let me just describe one other way to see this. It's nothing new, but it's just something you might like. So another reason why this is true is let's think of these letters as tiles, and what is this? 11 letters. So let's call them. Let's do M1, I1, S1, S2, I2, S3, S4, I3, P1, P2, I4. So if we actually have these 11 distinct letters, then the number of ways to rearrange them is going to be 11 factorial. However, if at that point we want to say, okay, let's consider all of the i's the same, then these four i's, instead of being, so within the four i's, there are 4 factorial ways to rearrange them. So we have to divide, but we're overcounting by 4 factorial. Similarly, if we want to say that these 4 s's are the same, then there's 4 factorial ways to arrange those that we have to divide out by. And same with these 2 p's, we have to divide by 2 factorial, and of course there's this 1m, which I'm going to leave out here, is 1 factorial. So that's just another way to think about why the number of distinct letters in this word is this multinomial coefficient. So you can write this out without even knowing that it is a generalization of a binomial coefficient. So I like this because with this word problem, it was much more natural, I think, to do it this way, whereas the problem with the policeman, it was much more natural to do it the way where you have 11 choose 1 times 11 minus 1 choose 4. So you have one policeman doing the job that starts with an M, machine work, I don't know. 4 policemen that get assigned the job that starts with an I, ice cream shop, I don't know, I'm going to just stop. And then 11 minus 1 minus 4, choose 4, that's for the S's, and then 11 minus 1 minus 4 minus 4, choose 2, and of course this is 11 choose 1 times 10 choose 4 times 6 choose 4 times 2 choose 2. So to me, I don't think it's very natural that when I look at this word problem to think of it like this. This is a lot more natural. But for the policeman problem with the donut shop and the paperwork, I think this was the more natural way to do it. When you write out the formulas, you see that things cancel and you get this. Okay, so two very different ways to think about basically the same type of counting problem behind the scenes. That's our first example. I want to do one more. It may seem a little bit weird, but there's a reason why I'm doing it. And if you wait till the next lecture on multisets, you'll see why I'm using precisely these symbols. Our second example is how many length 13 strings can be made using 6 instances of an asterisk or a star and 7 instances of a vertical line or a bar. So examples include star, bar, bar, star, 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 bar, 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 star, star, bar, or you can have 6 stars followed by 7 bars, or you can alternate them, bar, star, etc. So I don't know about you, but I learned about this when I was at college in 18, 19, 20, and it didn't strike me as strange at all, the terminology of stars and bars. I went to school in California, and then I moved to South Carolina, and I started teaching this in my late 30s, and I was like, wait a second, stars and bars, that is the nickname of the flag of the American Confederacy in the 19th century Civil War. This is the pro-slavery part of the U.S. that broke off. Now, I know I have listeners and viewers of this all over the world who might not know about that part of American history, but I certainly was wondering, how did this get this stars and bars, this pro-slavery flag? Like, how did that slip through the cracks? And was that just my classroom? So I Googled it, and no, it is actually a well-established combinatorial problem of stars and bars, and it dates back to William Feller. If you go to Wikipedia, if you Google stars and bars, one of the first things that comes up is combinatorics on Wikipedia. And William Feller, who was born in 1906 in the Austro-Hungarian Empire, now in Croatia, born in Zagreb, he's the one who came up with this. And the reason for doing it is because this is something that we'll see in the next lecture. He wanted something to denote, the bars denote dividers of different regions, and the stars represent different objects. So we'll see this next lecture. But suppose you wanted to select things from a vending machine, and you have Coke, Sprite, water, and then, I don't know, Dr. Pepper. And you wanted to pick 8 drinks. So you can pick, so one way to do that is you pick 2 Cokes, you can pick 1 Sprite, you can pick 3 waters, and then 2 Dr. Peppers. So you can describe this using a string of stars and bars. So that's where the notation comes from. It's certainly, I didn't find it funny the first time I saw it, but I did 20 years after that when I started teaching it in the South. Okay, so this is something that we know how to do. We know how to count the number of these. The answer is just a multinomial coefficient, 13 factorial divided by 6 factorial times 7 factorial, which is more commonly known as 13 choose 6, or 1716. Okay, so the reason why I showed this particular example is because we will use this, stars and bars, in the next lecture when we study multisets. So this comes up in that so-called vending machine problem that I showed you, where you want to pick k objects from n choices, but unlike when you pick k objects from a set of n, you aren't allowed to repeat. When you have a vending machine, you can repeat. You can pick multiple Cokes or multiple Sprites. So those are multisets, and that will be the topic of the next lecture. But before we do that, I want to have one last word about multinomials. And I want to at least show you the multinomial theorem. We're not going to prove it like we did with the binomial theorem, because it's a lot more complicated, and really it doesn't come up all that much. So multinomial coefficients, as I've told you before, they generalize binomial coefficients, which are the special case when r equals 2. Not surprisingly, the binomial theorem generalizes to a multinomial theorem. And I'm just going to show this to you for completeness or for fun. Take your pick. I think it's actually really cool. It's worth seeing. So it says for any variables x1 up to xr and integer n bigger than 1, if you add up those variables, so x1 plus x2 all the way up to xr, and raise it to the nth power, then you get, well, this creature. And what is this? This is a whole bunch of terms of the form x1 to the products of the variables, x1 to the n1, x2 to the n2, all the way up to xr to the nr. And the coefficient of this monomial is just a multinomial coefficient. N choose n1, n2, all the way up to nr. And we get one of these terms for all possible values of the exponents, ni's, where they have to add up to n. So I know this looks complicated, but let me first compare it to the binomial theorem, which just says x plus y, so we don't need x1 plus, so it's easier to use x and y if just n equals 2. To the n is just, so here we just have x to the k, y to the n minus k, so these things have to add up to, the exponents add up to n, and then we get the coefficient is the multinomial coefficient, n choose k, comma, n minus k, better known as n choose k. Okay, so let's do an example so we can really understand what this is about. So let's do, let's see, x plus y. I'm going to do x plus y plus z instead of x1 and x2 and x3. Raise this to the fourth. So what all this is saying is that we're going to get a whole bunch of terms that are products of x. So we're going to get an x to the fourth times, I'm not going to write it, y to the 0, z to the 0, plus x cubed times y, plus x cubed times z, plus x squared times y squared, plus x squared times y times z, plus x squared times z squared, plus, I hope I'm not missing one of these. I trust you can catch it if I am. X times y cubed, plus, so we're going to get term, and I'm leaving space here because I'm going to fill these in, x times y squared times z. We're going to get some terms of the form x times y times z squared. We're going to get some terms of the form x times z cubed. We're going to get some that are of the form y to the fourth, some that are of the form y cubed, z, some that are of the form y squared, z squared, some of the form y times z cubed, and finally we're going to get one of the form z to the fourth. And what this is saying is that the coefficient of each of these, so the coefficient of x to the fourth is just going to be 4 choose, I didn't leave myself very much room, 4 choose 4 comma 0 comma 0. So 4 comma 0 comma 0, that's just going to be equal to 1. Similarly, let me just go down. I'm not going to do all of these. So this one is the multinomial coefficient, 4 choose 1 comma 1 comma 2. This is 4 choose 1 comma 2 comma 1. Again, I'm just taking the exponents of these things. So up here we have 4 comma 2 comma 0 comma 2. Here we have 4 choose 0 comma 4 comma 0. That's just going to be 1. And I think you get the idea. Here we have 4 comma choose 2 comma 1 comma 1 and so forth. Okay, so one more, 4 choose 0 comma 1 3. So that's all this is saying. It's just a generalized way to write out a product of a bunch of variables. So instead of using binomial coefficients, that's actually where the name comes from. Binomial is for product of 2 variables, and multinomial is the product of more than at least 2 variables. Okay, so that's all I wanted to show you in this lecture. And I've already told you what's coming next. I think it's a really cool topic. It's on multisets. So be sure to stay with us, and I hope that I don't want to say see you then, I hope that you will see me then. Okay, so stay with us.